Some are people that you know. Mark Hancock was actually here at the end of the meeting last 20 years ago. He's now at UCLA. I don't think Dave Hunter's ever been here, but I think some people know him because they have been or are at Penn State. Steve Goodrow is a biological anthropologist at the University of Washington. So both Mark and Dave are statisticians. Carter is a sociologist, but a rather unusual one from UC Irvine. Pavel Kravitsky, I just had to put that down, University of Wollongong. Does anybody here know the University of Wollongong? Good, good. So he's down your way. So you should check him out. He's a pretty cool guy. He's done a lot of the newer work in this area. And what's that? Anyway, and Sky Benderdemal, who is at large. He sort of is an independent consultant, but does a lot of network visualization. So I started out by thinking that I had a kind of somewhat orthogonal development in literature and realized after Monday that this is really a completely orthogonal literature. I haven't heard anybody mention any of the work in this field. And I think it's in part because it doesn't focus directly on epidemic modeling, but it is, I believe, relevant. So the focus here is really on the contact structure, which we see as independent of the whole process of disease transmission, at least initially. That's the primary focus of the model. And the primary data that we use are then behavioral measurements on the presence or absence of these contacts of interest. The relevant type of contact depends on the pathogen. I really liked Brian's comment yesterday about case law. Not all networks are the same. It's not like you can go scrape the web and you've got social networks and you can spread diseases on those. The type of contact really depends on the type of pathogen that you're working with. And the goal of this particular analysis is to test hypotheses about what the underlying generative models are that produce these networks. The process of link formation and dissolution. It's an empirical approach. With respect to epidemic modeling, the methods generally then lead to simulation or algorithmic-based approaches, not analytic, but I'm putting yet there, hoping that maybe at some point that's where this work will lead. So the key idea is essentially people come and go, links form and dissolve, but if you characterize a network, what you see is that the structural patterns often remain. Not always, but often. And it's those structural patterns that we're actually interested in. What we're trying to do then is model what a social scientist would call this micro-macro link, how the local rules that individuals use to establish ties lead to the global structures that we observe, and then in turn how the global outcomes select for local rules. And the talk that I'm going to focus on here, the work I'm focusing on, is really the first part rather than the second. So I'm going to spend a fair amount of time talking about the origins and development of the statistical exponential random graph modeling framework, which really started in 1981, which wasn't that much before the Newton workshop. And it was kind of perking along under the radar at the time. The primary focus of the talk is then going to be on equilibrium models for prevalent ties, which in some ways are the least interesting models, but because they have so much of the structure that's going to be necessary to then do the temporal modeling, the dynamic modeling, I'm going to spend most of my time here because that's the foundation. And then work my way towards the temporal models that we now have for incidence and dissolution of ties. I'm going to talk a little bit about the public software that's available for this, the electronic resources, and some of the training workshops. And at the very end, I have a very short epidemic application. All right, so here's the problem circa 1994 from my perspective. We had essentially shown that network structure can influence the transmission of infectious disease. Lisa Sattenspiel's work on the movement of people across contexts through work, school, and home was a piece of that. There were models for percolation on lattices, though how many people here live on a lattice? Right. There were selective mixing models, which were essentially focusing on various kinds of nodal attributes and activity levels. I was working in that area, as well as Carlos Castillo-Chavez, who's not here, Mayan Anderson, and Kupin Simon Jacquet. There was lots of work in that area that was going on. And the household models of Dietz and Becker that we've heard a little bit about from Thomas. But what we didn't really have was a general modeling framework and empirical data to evaluate it. So during the workshop period, I ended up taking my first trip to Uganda. I was working on developing a survey of sexual networks down there. And I went with my kind of preconceived notion of what was important. for HIV transmission in Uganda. And in particular, what I thought was critical there was the sort of asymmetric age mixing, older men with younger women, which was sort of this conveyor belt of ensuring that a highly infected older population continued to infect a younger population, which would then infect their age peers, et cetera. But when I got down there and presented this model, one of the local audience members there said, can your models handle people having more than one partner at a time? And I was using the standard deterministic compartmental models with age structure, and the answer is no. They can't represent that explicitly. They can't represent partnerships, and therefore they can't represent concurrent partnerships. So that kind of changed everything. And one of the things that it did was, as a social scientist by training, I mean, I have a master's degree in stats. I had worked pretty hard on developing these age-structured compartmental models, and that one question kind of blew all of that out of the water. So I came back here wondering, okay, now what? And Hans actually connected me with a mathematician in the Netherlands, Miriam Kretschmar, and we proceeded to try to model some of these things. So this talk is not about what we modeled there, but it is in part the result of how all of this fell apart, why I stopped sort of trying to take this approach. So that by the end of the workshop, we had what was called Judgment Day. I'd forgotten that you had referred to it as such. So as we were being pronounced judgment on by Dennis, Valerie, and Brian, there were a number of comments to their talk. And in my comment, I basically said, well, yeah, we've got these log linear models for mixing matrices, but you know, there are these new things, these Markov random graphs. Logistic regression, I thought, was kind of the way to handle Markov random graphs, and we were going to be able to make some progress that way. So that was the direction. And what that was coming from, those Markov random graphs were actually sort of part of a tradition that had started in 1981 in an article in JASA by Paul Holland and Sam Leinhart, where if you take a random graph and represent it in its adjacency matrix form, as Thomas showed, with zeros and ones showing the presence or absence of a contact or a tie. For a directed graph, you can have an asymmetric pattern here, where if A nominates C, say with friendship, C does not have to nominate A in return. I can call you a friend, but that doesn't mean that you have to call me a friend. So this is an undirected graph that they were developing these models for. And the kinds of features that they wanted to capture were the variations in the row sums, which are the out degree distribution, and the column sums, which are the in degree distribution, and then the pattern of what they called mutuality, which is how often is it that when A nominates B, B will also nominate A. And the idea is to develop a model for the probability of this network, which they call the P1 model, also sometimes represented as the probability that the graph takes this form, or just the probability of G, the random graph. And the model that they developed is the simplest model. In fact, they wanted to denote this by P1 to emphasize that it's the simplest family of distributions on what they call digraphs. And it is a function of a term representing overall density and a parameter for that. Terms A sub I, those are parameters for each node in the network on their out degree. Parameters for each node in the network on their in degree. And then finally, a mutuality term here. A single mutuality term with a single parameter. So these are node-specific terms, but this is an overall network tendency, and this is also an overall network tendency here. C, inverse here, is a normalizing constant that means that that whole thing will sum to 1, so it's a proper probability distribution. C, it turns out, is not just a constant, it's actually a function of all of the parameters that you've estimated, and that turns out to be where a lot of the complication comes from, as we'll see. So the basic family that they are working from, you can call exponential family random graph models, or ERGMs, and that's what they're now called in my field, which is a really unfortunate acronym, but that's what we're stuck with, which is the probability of observing a graph or a set of relationships Y on a fixed set of nodes. In its most general form, that probability, given theta, is just an exponential form here. So this is a linear model in an exponential form with this normalizing constant in the denominator. The G of Y those would be your typical sort of predictors in a model, except in this case your predictors are network statistics, and we'll talk about what kinds of network statistics you can use. Theta is a vector of unknown model parameters that you're going to estimate, and then the k of theta, as we said, is the normalizing constant. It's the numerator summed over all possible networks on the node set Y. So, exponential family model, it's supposed to have very well understood statistical properties. It is, in fact, very flexible and very large class of models. But the thing I want to point out here is that what this normalizing constant requires is summing over all possible networks on the node set. Well, if there's 7 nodes, that means there are 21 dyads. That means there are over 2 million graphs that you have to sum over, and that's for a 7-node network. Okay? So that is going to be the source of some of the concern. It turns out that there is, with a little bit of algebra, you can show that that probability of the overall graph can be re-expressed in a conditional probability of a tie. So it's the conditional logit here of a tie. And it takes the log of the odds that yij equals 1 given the rest of the graph, yc, y complement, over the probability that yij equals 0 given the rest of the graph. And again, with a little more algebra, you'll find that what this resolves to is the same theta that we have from the model here, so our parameters are intact, times this delta g of y. So what's the delta g of y? That is the change in the network statistic when you toggle this one tie on or off. So how many new network statistic configurations of this form do you get when you make that toggle? We call these the change statistics. And note that one of the nice things about this form is that the normalizing constant has disappeared, and that gave everybody a false sense of security for some time. So model specification then takes the form of figuring out what terms you want in your model. So those are the network statistics. What do those terms look like? Well, you saw some of them in the Holland and Leinhart model, right? So they had the total number of edges, the density. They had a term for the degree for each node. They had a term for mutuality. So those were all there. So all ties, there's your typical density term. But you can have within group ties. So it's yij times an indicator for whether the two nodes are in the same category. You can model 2 stars, 3 cycles. This is essentially any kind of configuration that you think might have an impact on the probability of observing this graph is something that you can put in the model. And there's a basic distinction between 2 types of terms. Terms that we call dyad independent, and 1 and 2 here are dyad independent terms, and dyad dependent, 3 and 4 are examples of those. Dyad independent terms mean that the probability of the tie is a function purely of nodal attributes, other propensities, not other ties in the model. So they're independent of other ties in the model. And you can see that in the network statistic and also in the change statistic, there is only one dyad that's represented in that sum. It's not a product of dyads. So once you start getting these products of dyads, as you do in the 2 stars and the 3 cycles, that implies a kind of dyadic dependence, that the state of one dyad influences the state of another. And those turn out to be the more interesting terms, but also the terms where we've had some problems. So model specification is going to be about choosing the set of network statistics that you want from a simple sum of ties or products of ties to much more complicated functions, and you'll see some of those in the later part of the talk. And then choosing what we call the homogeneity constraints on the parameter theta for each of these statistics g of y. So for example, if you were just going to look at ties, not products of ties or products of 3 ties, but there's ties themselves, the homogeneous model for ties just says that theta ij then equals theta for every tie. Every tie has an equal probability of being present. Or you could classify these group specific by sex or age, for example. So theta ij is given a particular, and you, I think, referenced this when you were talking about your adjacency matrix. Some people call this the beta model. So it's a product of the propensities of if you're in group I or propensities if you're in group J. And finally, you could have just dyad-specific thetas. That's a saturated model, so every single tie has its own theta. Not obviously a parsimonious model, but you have that level of flexibility. So how do you interpret the parameters then that you're estimating these thetas? Well, at the graph level, the way to interpret them is it's the change in the log likelihood of the graph if the number of this type of configuration increases by 1, so that's at the graph level, the probability of the graph. At the tie level, it's kind of like logistic regression. So most people, when they talk about ergoms, they talk about it in this sort of conditional log odds probability. The change in the conditional log odds of a tie being present if it creates the network configuration of interest. Right? So if the theta is negative, then it reduces the probability that that tie exists. If the theta is positive, it increases it. So note that in contrast to a logistic regression, in this case, toggling a tie can have an impact on more than one network or change statistic, and it almost always does. So these will tend to be fairly highly correlated statistics. And especially, in fact, only for dyad-dependent statistics, if you toggle a tie, you can create a change statistics that's greater than 1. So if you're looking just at the edges term, the change in an edges term, if a tie is toggled from 0 to 1, will always be 1. It'll either be +1 or -1. But if you're looking at a triangle term, when you complete a triangle with a tie, it doesn't just have to complete one triangle. It can complete another triangle, and another triangle, and another triangle. And the same with a star term. If you add a tie to an existing star, it completes, if that star had already 4 ties, so it was a node with 4 ties, it creates 4 choose 2, 2 stars, 4 choose 3, 3 stars, etc. Right? So the number of the change statistics for dyadic dependent statistics turn out to be a little bit more complicated. And that turns out to matter for how you represent them. So the Markov ergms, that's just the kind of introduction to this general class of models. So when Frank and Strauss first proposed these Markov models for exponential random graph families, this was in 1986. This was really the first model for dyad dependence. So the Holland and Leinhart model had the mutuality term in there, and that's for ties within a dyad, right? But this is the first actual model for dyad dependence. And they posited, so start with this kind of theoretical assumption, kind of obvious one as a first start. Ties are conditionally dependent in a network only if they share a node. Otherwise, they're independent. Okay, so that's a baby step out towards thinking about dependence. This defines what's called a dependence graph. Some of you who are familiar with the graphical model literature, I'm talking about the dependence graph in that set. It's sort of like a line graph for those of you who are familiar with graphical theory more generally. But the dependence graph basically is a graph that specifies the nature of the dependence in sort of a graphical form. And the sufficient statistics for this Markov model turn out to be, in the graphical model sense here, defined by the cliques in the dependence graph. And that comes from something called the Hammersley-Clifford theorem, which was first applied by Julian Bisek. And that was where Frank and Strauss sort of got their start as well. So it turns out if you take a look at the dependence graph for a Markov model, the sufficient statistics are the ties, so that's a clique, clearly. What are called k-stars, where k is the number of edges incident on a node. So this is a clique, and this is a clique. And finally, triangles. That's the last clique that you get in a Markov dependence graph. All of these are for an undirected graph. So that seems like a nice kind of simple model, right? So in its general form, we've said nothing about parameter homogenization yet. In its general form, the Markov model has way too many parameters to estimate. Because for ties, you have n choose 2 parameters. You haven't made any homogeneity constraints on these. For the k-stars, you've got n times n minus 1 choose k for each of the k-stars, right? So that's a lot of terms there. And then you've got n choose 3 possible triangles. Each one also has possibly the same, a different theta. So that's a lot of parameters. So Frank and Strauss imposed some natural homogeneity constraints. This is the first time out of the box. You figure, okay, you want to start simply. All isomorphic configurations, so all triangles, all ties, all k-stars. Each k-star is equally likely. Each triangle is equally likely. And that leads you to a model that has a much simpler form. So there's a single parameter for, again, the density term here. So all ties are equally likely, conditional on the other terms in the model. Every k-star here is equally likely, and that's the theta that describes that change in log odds. And then all triangles have a single parameter as well. And what this does is it reduces the number of parameters down to a total of n, which is still a lot of parameters, probably a lot more than you would want. So things are getting almost interesting here. You get to part 4 of the paper where they start talking about inference from Markov graphs. And I read through this part kind of quickly at the time, which turned out to be a mistake. So standard likelihood techniques for the Markov models are not immediately applicable because of the complicated functional dependence of the normalizing constant c on the parameters. If the number of vertices is less than, say, 6, that should be a giveaway right there. It is feasible to evaluate C by direct enumeration. Otherwise, fitting the model to data can be a difficult problem. In this section, we indicate some possible approaches. Well, in the end, so they did indicate a couple of approaches having to do with graphs of size 6. And when they got two larger graphs, right, exactly. They punted and they used something called pseudo-likelihood here, which is basically just using logistic regression on the ties, observed ties, on the change statistics for the network terms that you have in the model. It's just a logistic regression, right? So that seems easy, and everybody was kind of excited by the fact that you could actually use existing tools to estimate these models. Because of the conditioning, though, in the conditional log odds form for this probability of a tie that leads you to the logistic regression form, what this ignores is the global dependence. You get the local dependence, but you miss the cascading global dependence. In addition, even though they used this very simple approach, they used a graph of size 30, and they set all the other parameters to 0, and they still had trouble estimating it, right? So that should have been an indication that there was a problem, and difficult problem turned out to be a massive understatement here. Some of you may remember that the MCMC estimation approaches were actually just being developed around that time. So the Geyer and Thompson paper came out in 92. We were here in 93. So people got excited about this and thought, okay, well, we can use this instead of that logistic regression approach. And they started using MCMC to try to estimate these homogeneous Markov models, and nothing good happened. They couldn't get the models to converge, and if they did converge, they converged on parameter sets that made no sense. So they made the models simpler and simpler and simpler, and the results got worse and worse. And so people began to question whether maybe there might have been something wrong with the MCMC theory in the first place for this kind of likelihood estimation. Maybe there was something weird about networks. And we spent about 10 years in the wilderness after that, trying to figure out what was going on. And what was actually going on is what you see in this model, which we call the stealth bomber plot. And essentially what's happening is these dyad-dependent terms behave very differently than we expect. They look simple, but they actually have these cascading processes across the graph because they're kind of a complex system component. The homogeneous Markov terms turn out to be some of the worst offenders. And what you end up getting when you put these in the model, especially if you have a very simple model. So this is the parameter space for a very simple model, just the edges parameter and the 2-star parameter. And what you're seeing here is what Mark Hancock called the degeneracy probability map, which is for all of the dark region, this pair of parameters in that simple model will generate networks that 99.999% of the time are either empty or full, or they have exactly one edge, or exactly one 2-star, or the maximal number of 2 stars. You know, so there are configurations that you wouldn't see in practice. And the only part of this parameter space that has any interesting graph is the part that's light. So that's what we're trying to do our likelihood estimation on. So this was Mark's way of putting it. The simple way of putting it is this model would not have produced the graph you observed. And because it's using MCMC, which is kind of a dumb sniffer dog approach to estimation, the sniffer dog gets really confused, and so you go off these kind of cliffs and can't get back to trying to estimate something that would be close to the graph that you observed. And there's some really nice recent work by Alessandro Rinaldo and Michael Schoenberger on this. So the solution is better network statistics, and because I don't have very much time at all at this point, I'll just say what we've done here, I'll just give you a flavor for this. This is a model now where the network statistic, it looks fairly complicated, but it's the geometrically weighted edgewise shared partner distribution. Essentially, it's like, think about a degree distribution for people. Now instead, take an edge and say how many shared partners does each edge have? okay? And subject that to sort of declining marginal returns for each additional shared partner. And one of the things you've just done is you've bounded that dependence. So it's no longer the case that, as in the old statistic, where each additional triangle that a tie creates contributes an equal amount to the likelihood. So if the more triangles a tie creates, the better. Now you have these declining marginal returns. And that allows you to do some really nice things. So I'm going to give you a sense here just of what kind of modeling we do. Well, we do clustering, for example, of mutual friendships. This is real data. It's data from the Ad Health study, which is wave 1. There are 90,000 students in it in 80 schools. And in each school, we have asked students to nominate their 5 best male and female friends. So here we're looking at the mutual nominations. And if we're looking at this clustering, we might be interested in 2 different processes that would generate the clustering. One would be homophily, which is people tend to choose friends who are like themselves. So you end up getting clustering, and even triad closure is kind of a byproduct of that homophily process. And the other is transitivity, which is, friend of a friend is my friend. So we end up using this approach to kind of distinguish between homophily, transitivity, and some ties, of course, do neither, and some ties do both, by comparing 4 models. This is the Bernoulli random graph. A graph or a model that just has nodal attributes in it, so none of the dyadic dependent terms. A model that just has the transitivity in it, and then a model that has both. And the way we look at these models is we start with the data and the model. We estimate our model coefficients with the ergom using MCMC. From this, we can actually simulate networks now from that distribution. We use the same MCMC algorithm used in estimation for the simulation part. Simulated networks are going to vary stochastically around the sufficient statistics. We can then compare from all the simulated networks that we have from our model, what do the aggregate graph statistics look like compared to our original network? Not for the statistics that are in the model. We know those are going to fit, right? But for higher order statistics that we haven't put in the model, how well do the local rules that we've put in capture the overall global structure? So for an example, if we look at the Bernoulli model, here's the observed degree distribution. And from our simulated model, when we estimate the Bernoulli model, this is what we would get. Not a very good fit to the actual degree distribution, but not horribly bad. For the edgewise shared partner distribution, this is capturing the local clustering. This is what we would get. So a Bernoulli model does a horrible job in reproducing that higher order statistic. And the geodesic distribution, that's what we observe in the network. And here's what we get from the Bernoulli model once we estimate it. Also not a very good fit. You put all those together and you can see, all right, so the Bernoulli model doesn't do so well on this school. In fact, you can then compare the 4 different models here. So the Bernoulli model, the attributes-only model, the transitivity model, and then putting both in. And you'll just see quickly that as soon as you put attributes in, and this captures differential propensities for making ties as well as homophily, you get the geodesics right, which is kind of interesting. It wasn't what I expected, but you get the global clustering right. When you put the transitivity alone, so just the friend of my friend is my friend, you get the degree distribution right for the first time, and you get the local clustering with the shared partners right, but you don't get the geodesics right. And it's really only putting all of them in together that you end up getting all of those right. The Model 4 performs pretty well in schools up to a certain size, but once you get to about size 1,000, we start seeing that the geodesic distribution isn't matched very well there. So you've got some other sort of process that you need. And you can compare the parameters across all the different schools, which again, I'm already over time, so I won't. So let me just say a little bit about development at this point. So we made an enormous amount of progress over those last 20 years after getting out of the degeneracy problem. We now have temporal models for ergoms, which are models for tie formation and dissolution separately that are estimated jointly, that allow for vital dynamics, that is node entry and exit, as long as you specify what you want to have happen actually. Do you have the mean degree preserved as size changes, or do you have the density preserved? We have models for sampled network data. And we have a host of other models as well, latent class, latent space models, valued, signed, and weighted graphs, hierarchical ergoms. There are now packages called Hergom and Bergom, also on CRAN. These are written by people who were not part of our team, so the whole thing is kind of exploding. And in fact, at the meeting of network analysts this last year, which was in Hamburg, they did a bipartite graph here showing presenters by sessions And it turns out, if you look in the middle, what's in the middle of this graph, it turns out to be exponential random graph models. It's basically changed the field of network analysis in about a decade. And apropos, where's Julia? Ah, yes. So this is what our kind of the published items using ergoms and the citations to those. So this is clearly on also a rather nice upward trajectory. There's some public software from our team called StatNet. It's all up on CRAN. Functionality includes data management, analysis, estimation, simulation, visualization, network movies that are a lot of fun, which I don't have time for here. And we have an epidemic, not only an epidemic application, but we now have an epidemic modeling package, which will be put up at the end of this month, actually. So I'm excited about that. So I'm not going to go through all that. All I'll say is, once you've got this whole thing going, you can simulate networks now with different kinds of structure that you can really control at a very fine, detailed level. And that gives you an insane amount of data. And we've gone from a field as a result of we had no data to start with, network analysts, right? And now we've got we can simulate so much stuff to see how networks influence transmission. And basically, I would say, this is enormous progress from the stochastic network modeling standpoint. From the disease modeling standpoint, we're still using this as a foundation for simulation. And I think that's something. It's not nothing. It's not chopped liver, right? It's nice that we can now at least see. We have a laboratory. But it's not analytic, and we would love to have something analytic. So, maybe this will at some point make it possible for us to do that. Thank you. Hello.
Hi.
Hi.
What you presented seemed to be in some sense for static networks, right? But you started out as speaking of sexual networks,
right?
Where the change over time might be important.
Exactly.
For us, at least.
Yeah.
Can you make sure you stand up and shout?
Yes. I said that the presentation seemed to be about static networks, but what about, say, sexual networks that change over time, and where you're interested in tracing links? And
Exactly.
changes?
Exactly. And I warned you that I was going to focus on the equilibrium static networks because that's where you get the machinery, right? So the tergums is where we do that. That's been the new developments. And the temporal models, basically, the version that we've been working with are separable temporal models. So there's a formation stage and a dissolution stage within step. And the formation model is just an ergom. So what are the things that encourage people to form a tie? The dissolution model is also an ergom. What are the things that lead to a tie being more or less likely to dissolve? And within each step, those are separable. But then at the next step, any ties that you formed at the last step influence what happens in the dissolution step next. And any ties that were dissolved in the last step influence what happens in the formation stage next. So that's a very quick sort of, yeah?
Have you tested these on longitudinal data or on cross-sectional data for age?
When now we get back to, how do these things actually work in the real world? We don't have a lot of longitudinal complete network data. So these models can be tested, but again, the number of data sets that we have, and it's only certain kinds of social contacts that we have that kind of information. If you wanted, for example, social media, there's tons of information now, but social media isn't what spreads HIV. So if you're interested in HIV, what we don't have is empirical data on longitudinal sexual networks. But what we do have, using this approach, if we assume that the networks are roughly in equilibrium, we can take a cross-sectional egocentric sample, which is an incredibly convenient way to try to sample these networks, with information about the duration and parameterize a tergum from that, which is kind of remarkable. So with very little data now, we can parameterize complicated models. They're complicated in some sense, but in another sense, all they do is represent the things that you can observe. They don't do more than that, right? So they allow you to investigate how the things you do observe and the data you can collect would influence an epidemic.
Okay, I think we're going to have to stop there, but thanks very much, Martina.
Thank you.